Okay, so we'll start this lecture off with an approach at finding things at equilibrium and solving for equilibrium constant. That is a method that you're more used to, because we're going to use the 162 method, right? Where we can use our coefficients and what we actually have along with our new way of determining what our equilibrium constant is. So this question gives you 2 moles in a 2-liter flask of hydrogen iodide, and that reaches equilibrium and produces 0.214 moles of iodine gas. So we want to know what the concentrations are of the HI and the hydrogen gas and what the equilibrium constant is. So I can start this off and I can look at it and be like, okay, let's start with our equilibrium equation. And this pen is going to be the bane of my existence the entire quarter, isn't it? All right, here's Kc. And it's going to be the product of the products divided by the concentration of the reactants. So here is my H2 gas. There's a 1 coefficient in front of it in the I2, so it is raised to the 1, if you will, divided by the concentration of HI. And this quantity will be squared because of the 2 coefficient in front of that. I want to remind you, though, that this is at equilibrium. So that initial concentration only helps us figure out how much it changed by, or what our final concentration is of the HI at the end when we're at equilibrium. Other than that, we're not going to use that to determine how much of the H2 or I2 we have. Okay, so my I2, what do I have here? I'm told that at equilibrium, I have 0.214 moles of my I2. Well, that's kind of nice because it's 1 to 1. So however much of the I2 I have has got to be the exact same amount of moles of the H2 I have. That'll be 0.214 as well. I can do something here. I can figure out how many moles of the HI it took to get to the 0.214 moles of the H2 and I2. And I can use my stoichiometry to get there. So let's go ahead and take a look at that. I have 0.214 moles of I2 times, let's see, to get to moles that I've used of the HI, I have 1 mole I2 to 2 moles of HI. Now, we are doing these things in terms of concentrations, so I have a couple of choices here. I eventually want to get to moles of HI. So moles of HI, what is that going to be? Moles of HI. That is going to be the initial moles minus the used moles. Will give me the moles of HI at equilibrium. Okay, this calculation here gives me the moles used. So what am I going to have? That's going to give me 0.428 moles of HI used. So 2 moles of HI minus my 0.428 moles used will give me how much I have of HI at equilibrium. So 2 minus 0.428 tells me that I have 1.572 moles. Cool. Okay, so I know at equilibrium I have 1.572 moles of HI. Let's write the units there. Because the one thing we haven't done is turned these moles into concentrations. So remember, Kc is in terms of molarities, not in terms of moles itself. This 1.572 moles then for the HI concentration is going to equal my 1.572 moles of HI divided by my 2 liters, 2.00 liters of HI. So 1.572 divided by 2 gives me 0.786 molar. For my I2 and H2, I only need to do the one calculation because they're both the same amount of moles. So I'll have 0.214 moles of, and we'll go ahead and choose one, just I2, divided by my 2.00 liters gives me 0.107. I don't need to do a calculator. 0.0107 I do believe, though. 0.214 divided by 2. Yep. No, 0.107. Yeah, we're good. 0.107 molar I2 and 0.107 molar H2. That's molar. Okay, so what do I have? They wanted the equilibrium concentrations for HI and H2. I have that here and here. Let's take a look at our Sig Figs. Let's see. This is actually, I should have written this out, 2.00 moles minus my 0.428. So my 0.428, that's 3 after the decimal, but my 2.00 is only 2 after the decimal. So I'm only going to have 2 after the decimal, so 1.572 molar. 1.57, sorry. So 3 Sig Figs there, 3 Sig Figs there, so 3 Sig Figs here. And then 3 Sig Figs here, and 3 Sig Figs here. Cool. Now, the next thing we want to do is figure out what our Kc is. We have all of the values that we need. Kc then is going to be my 0.01 or 0.107 squared divided by the 0.786 squared. Now, why am I just squaring them both off right out of the gate? Well, because they're both the same molar concentrations, so they have the same molarity, so it's just the same value squared. The 0.786 is squared because my equilibrium constant had that value squared. So what do I get from this? I get 0.107 squared divided by 0.786 squared, and I get 0.0185. Kc does not have any units, so don't put any units in there. Unlike our rate constants where we worried about the K and the units that K had there, this we don't. So don't let yourself get sucked in and putting in units there. There, have we answered everything? Let's see, I have this. I have all of my concentrations, and we're done. Now, there's a different way that we can look at doing this, and that is to look at using this thing we call a rice table. But before we do that, I have changed the temperature, so the equilibrium concentration Kc, constant, has changed. Can we use the value of Kc, in this case it's 0.016, that hasn't changed by much from the last question. Can we use that value to determine how fast it takes it to get to equilibrium? Pause and think about it for a second and come back. Okay, so hopefully you came up with, we can't tell how long it took. Remember, when we're looking at time, those are going to be our rate constants. So there was that line that we drew on the graph, and we looked at the rate of change that was happening before it got to equilibrium. So our K tells us how much will be on the product and the reactant side at equilibrium, but it doesn't tell us how fast it got there. So it's an important fact to remember. We don't know how long it took. It could be really fast, or it could be like days or eternity. It could be forever. We don't know. Now let's take a look at this, and we're going to do some math. And the way we're going to do it is with this thing called a rice table. And what a rice table stands for is the R is for reaction. Reaction. The I is for initial concentrations. The C is for the change in the concentration. And the E is going to be the equilibrium concentration. What you're going to find is with a few pieces of information, we can determine almost anything about a reaction. We do need to have sufficient amounts, and you can think of it in terms of like the number of equations that you need for the number of variables. If I have 3 variables, I have to have 3 equations. If I only have 2, I can set things up, but I can't actually solve for everything, or in some cases, anything. So let's see how this works. We have 0.5 moles in a 5-liter flask, and we know what our equilibrium constant is at this 0.016 at 300 K. And we want to know what are the final concentrations of everything at equilibrium. And so let's set this up. The rice part, so the R, is to go ahead and write our chemical equation. 2HI, gas, and then that's going to go to my H2 gas and my I2 gas. That is my R. Let's change the pen color. I'm going to get fancy here. Okay. Now for my I, initial. So I have, let's go ahead and write this 0.50 moles over my 5.0 liters, 2 Sig Figs in both. I'm doing multiplication and division, so my molarity is going to have 2 Sig Figs. That's going to be 0.10 molar. So this is starting at 0.10 molar. H2 and I2, we're told only the concentration of the HI, so from there we can infer that we're starting off with nothing in the I2 and the H2 and the I2. So my hydrogen gas and iodine gas, there's nothing. It's not always the case, but you will have to be explicitly told that that's not the case. Okay, so my change. Now we don't know what that is, and before I wrote that we're taking out the amount that was used. Here, let's just denote that as X. And let's remind ourselves that every time this reaction goes through, I'm using 2 moles of HI. And let's see, I'm going to produce 1 mole of each of my products, but I'm going to use, so minus 2 times X, where X is the amount it's changing by. Now likewise, when I get over here, instead of losing some, whatever that 2x is lost, or whatever the HI is lost, these guys have gained. So I have a plus X on here and a plus X on here. The plus X and nothing in front of it just means that I have a coefficient, stoichiometric coefficient of 1. And so now my equilibrium, I can draw a little line, is going to be adding those 2 lines up, 0.10 minus 2x, X, and X. Now, in order to do anything with this, we need to come to our equilibrium equation. So we know what Kc is. We've been given that. And we need to write out what everything is that we have done on the previous slides. So we know that this is our Kc equation divided by Hi squared. Now all we need to do is take the information from here, because this is at equilibrium and Kc is at equilibrium. all of these values in this last line then go into our Kc equation. So I get Kc equals x for H2, x for I2, divided by 0.10 minus 2x. And that quantity is squared. This simplifies down then to Kc equals x squared divided by 0.10 minus 2x squared. Beautiful. It can be tempting now to throw numbers in there and solve a quadratic and then FOIL out this term. The easier approach, the kind of cheater approach, is to say, you know what, if I take the square root of both sides, those squares are going to go away, and I'll have the square root of Kc equals x over 0.10 minus 2x. Life got nice. Always look for those little things that are going to make your life a lot easier. Now the next step is we need to solve for x. Well, to do that, I need to get rid of my fraction and then get x on the same side, so I can isolate it and find out what its value is. So I'll get the square root of Kc times 0.10 minus 2x equals x. Beautiful. Now I need x on just one side of the equation. At this point in time, a lot of you are going to feel more comfortable to throw numbers in there, and you can do that. The reason I discourage it is what many of you found on the review homework is that you and your calculators aren't friends. So it is easier to cut down the amount of times you're going to button push. That will save you a lot of frustration when you're entering things in to SmartWorks. I was going to say Sapling, that's not right. So let's just kind of practice getting that set up. To get x on the other side, I'm going to distribute my Kc. So I'll get Kc is 0.10 times the square root of Kc. Let's make sure that's clear. Minus 2 square root of Kc times x equals x. I need the thing I want on the same side of the equation, or on a side of the equation. So I'm going to take this 2 times root Kc and move it over to the other side. I have 0.10 times the square root of Kc equals 2 root Kc times x plus x. Just added it to the other side. This is just like 3x plus 1x, except they're not pretty numbers, right? If they're real easy numbers, you just combine the two. The easier way to avoid that, because we have ugly numbers, is just to factor the x out. So I'll get 0.10 times the square root of Kc equals, I can factor the x out, and what am I left with? I'm left with 2 square root of Kc plus 1. And now finally we're ready to solve for x. So 0.10 times the square root of Kc. I can move this entire term over to this side. So I get 2 root Kc plus 1 equals x. Now I can put my numbers in. So I'm going to have, let's say, 0.1 times the square root. That doesn't even make sense, 0.1 times the square root, here we go, of 0.016 divided by 2 times the square root of 0.106, we got plus 1. If I have all of my parentheses right, cool. Then I get that x equals I want to double check that, 0.00766. Do I agree with this? 0.1 times the square root of Kc. No, I did that right. All right. This is then the change in the molarity that we have. That tells me what the concentration is here. So I know this. I don't need to do any more math with it. And these are both the same. 0.00766. My equilibrium concentration for my HI, though, I want to go ahead and do this equation. I already wrote the math out, so I just need to put in my numbers. So 0.10 minus 2 times 0.00766. So 0.1 minus 2 times of that gives me 0.0846. Let's see, that's sufficient. 68. Okay, let's take a look at our Sig Figs. I have 2 here, 2 here, so all of my answers are going to have 2. 2. And I can look at my multiplication and division for the numbers after the decimal. What I have to be careful here is I did factor out, so the 1 in front of the x is like considered an infinite amount of Sig Figs. So that's not going to impact anything. It doesn't mean I'm going to truncate everything on this line here to be 0 Sig Figs. So that's not going to impact my Sig Figs, this line here. It's the 2 after the decimal that are going to change things. So I'm going to have 2 Sig Figs in all of my answers. And finally, the double check that I can do that this math was done correctly. And the small number is what made me kind of a little bit suspicious that maybe I'd button push something wrong. Is that we can put this back in. And if I put it back in, I had better get the correct or the original KC that I was given. So 0.0076 squared divided by 0.08468 squared. And again, that's because this bottom one was squared. HI and I2 are both the same. So let's go ahead and check that, shall we? See if my nervousness over did I button push that wrong is confirmed. And there's this one. Woo! 0.00766 squared divided by 0.08468 squared. Okay, so I do have a mistake. So let's see. Where did I go wrong? Let's recalculate it. 0.1 times the square root of 0.016. There's that. 2 times the square root of 0.016. Here we go. Plus 1. And then this divided by that. There we go. Okay, so it was wrong. So let's change the color of the ink. The process was correct. My button pushing was not. And what's kind of nice there is gives you a chance to see the benefits of double checking, right? So this number here, when I originally put it in, I came up with a KC value that was like way off. 0.008, right? Which is not this 0.016. So that tells me that I didn't square something when I put it into my calculator. I made some sort of error. Okay, so what this should have been, I'm going to just draw a line through these values. What this should have been is 0.010095. There we go. 0095. That makes me feel better. So that makes, this is going to be different. So 0.1 minus 2 times that. Here we go. Gives me 0.0798. All right, again, we wanted 2 Sig Figs. That's 2, 2, 2. And so then this is wrong. And we'll go 0.010. Just do that squared divided by 0.0798 squared. We're just going to double check it again. Divided by U. Boom. Got it. So then we get KC does equal what it should equal. So let that be your lesson. It happens to all of us. Calculator button pushing errors do occur. Don't assume that you don't know how to do it or that you did it incorrectly in your setup. Double check it and then put the values back into your calculator to find where your mistake was. For mine, I knew that all my manipulations to this point were fine. It was now just putting the values in. So it was just a couple button pushing steps to find the mistake, fix it, and now I've identified it. Honestly, it's going to save you a ton of time if you get in the habit of doing that. All right, let's do another example.